I'm Christopher Byerly. I'll be covering the Fukushima Daiichi incident located in eastern Japan. I'll be talking about a few topics. I'll be talking about the operation of the Fukushima Daiichi boiling water reactor. I'll be talking about operation, construction, safety, and containment. The Fukushima Daiichi plant contains 6 reactors. These reactors were made by General Electric and had a couple variations. So the Mark III, Mark IV, and Mark V were the different styles of boiling water reactor that they had. And they all performed the same function but slightly different. They had a few alterations to make them better and more efficient. I'm going to be talking about a few different points and differences between them. We'll be discussing the fuel assembly, reactor vessel, and the coolant system flow paths. The boiling water reactor fuel assembly is comprised of 3 major parts: the fuel, the control rod, and the cladding. The fuel is made out of uranium. This is what promotes the fission process. The control rod is made out of boron. It is very, very good at absorbing neutrons. And the cladding is made out of zirconium, which has a high resistance to corrosion and has a high melting temperature. How this works is the control rod is in between the fuel. When the control rod is fully inserted, it will absorb all the neutrons and stop the fission process. When you withdraw the control rods through the bottom, this promotes that fission process and allows that heat to be generated from the fuel and pass through the cladding. The cladding separates the fuel and the water so that radioactive particulates don't get from the fuel to the water. The difference between the Mark III, IV, and V is the amount of fuel assemblies. Boiling water reactor, or Mark III contains 400, Mark IV contains 548, and Mark V contains 764 fuel assemblies. The boiling water reactor vessel has a few major components. The reactor vessel head, which is removed in order to support refueling. The steam dryers, which dries out the steam before it goes to the turbine generators in order to not damage the turbine generator blading. The steam separators, which allows the steam that goes to the steam dryers to be mostly free of water before it goes to the steam dryers. The feed water sparger, which sprays the feed water into the core from the feed water system to allow even mixing. The fuel assembly, which was previously described. And then the core plate, which allows the water that is being recirculated in the loop to evenly be distributed to the fuel. The boiling water reactor has 2 main flow paths: the coolant flow path and the steam flow path. So the steam flow path is where the water is heated by the fuel and then is boiled and then sent through some moisture separators to the turbine generator as dry steam. The turbine generator then uses the mechanical power of the steam to turn turbine blades and generate electrical power. That exhausted steam from the turbine generator then goes to a condenser where an ocean or shore supply, like a lake, then sends water to the condenser and is pumped through the condenser to cool down that steam and condense it from steam to water. That pool of water that collects on the bottom of the condenser is then pumped to a heater. This heater is to increase efficiency and heat the water up before it goes back to the reactor core. Then through the feed water sparger is sprayed back into the reactor vessel. Now the water that is not hot enough to turn into steam is recirculated to ensure the fuel is being cooled. There are 2 major methods of controlling the boiler water reactor: control rods and then flow using the pumps, recirculating pumps. So to get the reactor to, from subcritical to about 30%, it's mostly done by withdrawing control rods, exposing the fuel, and having fission occur. From about 30% to about 100% is actually adjusted by increasing flow through the reactor. So the more flow that you have going through the reactor, you're removing more heat from the fuel. That fuel is heating up the coolant around it. The coolant is then forming steam going through the moisture separators and dryers to the turbine generators, spinning the turbine generator blading, generating electrical power, then condensing that steam, and then circulating it back through. So as reactor power needs to be increased, you just increase your flow. That'll increase your power, or you can withdraw control rods to increase power. The boiling water reactor has two methods of removing decay heat during normal operations while shut down. So with the rods fully inserted, decay heat is still generated due to radioactive particulates from fission. So due to those radioactive particulates, it still continues to heat up the water after shutdown. So the water that is in the core is heated up and boiled, like critical operations, then sent to the turbine generator, but in this case, the turbine generator is bypassed and sent straight to the condenser. The condenser then cools that water and then sends it back to the reactor vessel. The other method is the residual heat removal system, which taps off of the recirculation line and sends the water from the recirculation line to a residual heat removal heat exchanger, which cools off the water, then sends it back to the core, then recirculates that water. The emergency core cooling system is the cooling system that is ultimately responsible for removing decay heat when the reactor is shut down in an emergency situation. It's comprised of two major subsystems, the high pressure and the low pressure subsystems. These systems are then broken out into the automatic depressurization system and the high pressure coolant injection system. And the low pressure systems are core spray and low pressure coolant injection system. There are two subsystems, part of the high pressure subsystems of the emergency core cooling system, known as the automatic depressurization system and the high pressure coolant injection system. These systems use the steam from the reactor to put the reactor in a safer condition. So the high pressure coolant injection system uses steam from the reactor off the main steam line to drive a high pressure coolant injection pump. The pump is turbine driven, so it uses the steam to drive a turbine to spin that pump. That pump takes water from the condensate storage tank and the containment suppression tank, pumps that to the actual core to maintain the core covered. The other system, the automatic depressurization system, takes steam from the reactor vessel and sends it straight to the containment suppression tank and then filters it through the water in the containment suppression tank. This system is to depressurize the reactor as quickly as possible in order to put it in a condition where there is less pressure in the generator and the lower pressure systems can take over and continue cooling the core. The low pressure subsystems of the emergency core cooling system are the core spray system and the low pressure coolant injection system. These systems are meant to cool and keep the reactor covered when there is no steam present in the reactor vessel. So the core spray system uses an external power source and pulls water from the containment suppression tank, pumps that water directly into the core. This is to get water into the core and keep the fuel covered with coolant. The low pressure coolant injection system uses parts of the residual heat removal system to pump water from the containment suppression tank through the residual heat exchanger, residual heat removal exchanger, and then pumps it to a couple different places. So it pumps it to the containment suppression tank, also pumps it into the containment dry well through the containment spray, and then it also taps into the recirculation loop and pumps it into the recirculation loop to cool the reactor. The process of fuel meltdown begins when the decay heat being formed in the core and the fuel is not removed. So what begins to happen is the fuel temperature rises and rises and rises until it gets hot enough to actually melt the zircaloy cladding, and then it'll continue, if not cooled, to increase in temperature it'll get so hot to the point that it'll start melting the structure that is actually holding the rods. And it'll form in the bottom. It forms an element known as corium, and it begins to generate hydrogen gas. The reactor vessel will contain the corium until the point of where it reaches such a temperature that it melts through the steel of the reactor vessel and begins to release hydrogen gas into the containment. The Fukushima Daiichi boiling water reactor has two main containments, the primary and the secondary containment. The primary containment consists of a dry well with vents that go to a suppression pool that completely surrounds the dry well. That is considered the primary containment. The secondary containment is the building that is made out of concrete and steel that surrounds the emergency cooling systems, the spent fuel, and the primary containment. Thank you for watching my presentation on the Fukushima Daiichi plant boiling water reactors. I hope you stand more informed about a boiling water reactor and how they work and how the operation, construction, and safety features work for the boiling water reactor.